Recording is rolling. So have a bunch of stuff lined up this week. We're gonna kick off with the Kahoots. You guys remember the new stuff you guys learned last week, just the concepts. Then I'll go back and give you guys more notes on finish those homework puzzles. Okay. Here's the Kahoot 10 that's up and running right now. You guys are logging on to. Okay. You guys remember there's an AP classroom that's open. Now this technically closes like tomorrow at 8 a.m. or something like that. So just knock that out tonight. There's a lot I want to do with you guys later this week. We'll let you get to that. Right, so you guys know, do AP Classroom by tonight. If you have, some of you guys have already turned this in, so yeah, that's off your hands. Okay. There are these Chapter 5 puzzles. This is the guy with the motorcycle that are due Friday, and we went over some of those last week. We'll do some more today after the Kahoot. And I have a new open notes take-home quiz for you guys. That's due 1 week from now. It looks like this right here, and it's flipped to the front of your desk. Okay? So you guys see the one that says Energy Quiz AP. Okay, is the Energy Quiz AP? Okay. All right. Any questions so far? All right. Gonna flip over. Okay, present screen to share. Oh, look at all you guys ready to go on Kahoot. Oh, hold on. It's projecting my screen weird. Let me flip back and forth, see if it fixes that. Okay, well, I think we'll just make do with this for now. All right, you guys ready to roll on Kahoot?
Oh, wait, never mind. Take 2 months.
In physics, work is defined as work.
So like we can see it well.
Okay, yeah, here. Let me flip my screen, see if it resets. Right. Also, yeah, you guys remember? Here's another place you can see is. You guys remember this this table from last week? Okay. If you look on the back of this printed packet, you guys see all these questions? These are the questions we're doing. If you guys want to follow along, okay? Same questions.
It kicked me out. Oh.
All right, so the pin 5710582 should, okay, yeah, that looks better. Okay, so looks like our screen is fixed. All right,
Okay, there.
yeah,
Thank you.
yeah. We got Shane leading the pack, Natalie, Lucas, Fowl, and Paula. If Nellie Newton pushes with twice the force for twice the distance, oh yeah, you guys got this. Okay. So you guys know work is force times distance. So if you double the force and you double the distance, that's a factor of 2 times a factor of 2. That's 4 times the number of joules, right? Okay. Guys, I'm gonna try to go through this a little bit fast. But if you want me to write anything down, then let me know and I'll write some notes. Okay. Work. Oh yeah, look at that. Look at that. So you guys know that work is an energy transfer. Work, energy, those are measured in joules. Meters is displacement. Newtons is a force. Watts is power, which is a rate of work. All right, Lucas, Natalie, Shane, Isabella, JT. Power is defined as yeah, work divided by time. Work divided by time. Remember, power is a rate of work. Right? Work divided by time. That's joules per second. That's what watts are, right? This power is measured in watts. All right, Natalie, top spot. Lucas, Shane, Isabella, Jake. Unit of power. Watts, yeah. And remember, 1 watt is 1 joule per second. My classic go-to example is a light bulb. If it's 20-watt light bulb, that means it's pulling 20 joules per second off the grid. Got Natalie, Lucas, Shane is on fire. JT and Isabella. The amount of potential energy possessed by an elevated object is equal to work done lifting it. Okay, so you guys remember how work is force times distance? And if you're lifting an object, couldn't the force be equivalent to the weight, right? So whatever the weight is, you have to apply at least that much force to lift it. Right? And then the distance that you lift it, force times distance, couldn't that be the height change? Oh, wouldn't that be like mgh? That's what potential energy is, right? So the work, actually, I know I'm trying to go through this kind of fast. I'm trying to do a trade-off here. Okay, I will write this out. Okay, so remember how work is force times distance? Okay. So if you're lifting something, you have to at least apply its weight to lift it. And maybe the distance you move it is the height change. Oh, isn't that potential energy? So the work you do lifting something is equal to the potential energy that you end up giving it. Shane, Jake, Natalie, Lucas, Ian. Kinetic energy is equal to look at perfect. 1/2 mv squared. That's the energy of motion. All right, nice. All right, JT hopping in. Top 5, Shane leading. How much further will a car traveling 100 kilometers an hour skid compared to one going 50 kilometers an hour? That's to say, if the car doubles its speed, what happens to its braking distance? Yeah, four times as far. Like, why 4 times as far? Okay, yeah, this one I better go. So, sorry. Now, this one I talked about last week. You guys remember this energy table? I know we still got a couple of rows here, but something. All right. You guys remember this car braking to stop? Braking to stop. See that? Okay. Ooh, look at that Halloween face. So why is it that if you double the speed of the car, it's 4 times the braking distance? What's that about? Well, it's work energy theorem. So the sum of energy initial is equal to the sum of energy final. Okay. Now this is true for a closed system, but if it's an open system, then you might say, well, A plus the work done on the object plus work. Right. So okay, so the initial energy plus the work would be the final energy. Okay. And for the car, wouldn't it be all 1/2 mv squared? Because the car is in motion, maybe be not its initial, right? Okay. The car's in motion, so it has this kind of energy. I don't see any hills, so no potential energy. I don't see any springs. Okay. Isn't the work done by friction, which would be force times distance? Now, that would also be negative work. I'll just go ahead and slap in the negative sign at this point. Friction force times stopping distance. So that the car ends up with 0 joules of mechanical energy. Right? And if you like, you can even think of it this way. I'll do one more step, show this proportion. The initial kinetic energy all goes into work done by friction. So I did one algebra step there. I just added this term over. Right there. Okay. Now, the question that you guys just answered on Kahoot says, what's the relationship between the initial speed of the car and the stopping distance? And it framed it in a way like if you double your initial speed. Guys, if you throw a factor of 2 on that V, doesn't that factor 2 become squared? So wouldn't the car have 4 times the initial kinetic energy? Right? And the friction force doesn't change. So that factor of 4 is all routed into the stopping distance. Okay. What if you triple the speed of the car? What happens to the stopping distance? Increases by a factor of 9, right? Because 3 squared is 9. Okay, so, okay, so back over to here. All right, we got Jake, Natalie, Lucas, Shane, Isabella. An arrow in a bow has 70 joules of potential energy. Maybe think like spring energy, sort of. How much kinetic energy will it have after it's been shot? Yeah, okay, yeah. So conservation of energy, 70 joules. So all the joules from the bowstring go into the motion of the arrow. All right. Natalie, top spot. Lucas on fire. As the pendulum swings back and forth. Yeah, all true statements. You guys remember Paul Hewitt about to get smacked in the face with the bowling ball? But he didn't, because conservation of energy. So at the end, at the high points, it's elevated, has potential energy. At the low point, it's in motion, kinetic energy. It swaps back and forth between those two. Potential, kinetic, potential, kinetic. All right, Natalie, keeping the top spot. Oh, when a car speed triples, it's kinetic energy. Yeah, it increases 9 times because 1/2 mv squared, right? 1/2 mv squared. If you square that speed, right? Factor 9. Right? Maybe I should put this question before the breaking question. Probably made more sense to split into that. I got Natalie, Jake, Lucas, Shane, and Cam. One job is done slowly. An identical job, say same number of joules, is done quickly. Those jobs require different amounts of what? Right. So, oh, hey, nice. Right. So, yeah, this one you have to read into a bit. There's only so much Kahoot space for text, but that word identical. What's really going into that? In here, the implication is like the same number of joules, like the same work. Right. So if it's the same task, the same work, maybe you're lifting some object, some height. So MGH is the same for both. Right. But power is work divided by time. So if you do if you do this another job more quickly, is that more or less power? If you do it faster, it's going to be more power, isn't it? It requires more watts. Maybe you have some machine connected to the grid, it'd be like more wattage. Think of it that way. Right? It's divided by a smaller time interval. All right, Natalie, keeping that top spot. You can beat Natalie. Which requires more work, lifting 70 kilograms up 2 meters, or something with half the mass, therefore half the weight, up twice the distance, twice the height. Huh. Oh, look at you guys. Right, so you guys know MGH or force times distance. Either way you think of it, if one variable gets cut in half and the other one doubles, those two cancel out. You guys got it. Nice. All right, Isabella hopping in. Natalie's still in the lead. An object that has kinetic energy must have momentum. Okay, tell you guys what. All these questions I'm actually drawing from Paul Hewitt's materials, and he actually teaches momentum before all this stuff. So, do you guys see that the fact that momentum is mass times velocity, and we'll talk about this in the future. This is actually an upcoming topic. Look at the ingredients that go into that, right? Mass and velocity. Hey, aren't those like the same ingredients that also go into kinetic energy, 1/2 mv squared? Right? It's like the same start, right? It's like you're just baking a different cake with like flour and eggs and sugar, right? Now, acceleration is a rate change in motion. You don't have to have a rate change in motion to have any 1/2 mv squared, right? You just have to have a speed and a mass, right? And same idea with force. Now, if there's a net force, it would be accelerating. You definitely don't need that. In fact, what about Voyager 1 spacecraft? Is there any force on Voyager 1 spacecraft? No, it's just going, right? Can it still have kinetic energy? Yeah, it can have mass and speed, 1/2 mv squared. That's all the ingredients you need. Okay. Oh, Jake, moving to the top. Shane, on fire. Natalie, Lucas, Rita. A pulley system can... Oh, nice. Yeah, I need to reword that one, but yeah, you guys got that. So multiply the force. The idea of that is a mechanical advantage. But if you pick the yellow one, then well, that includes that too, right? Okay. Of course, you could change the direction of the force. Right? Yeah. So the reason the red one is wrong is because even though you could make a case for this, you could say like, oh, if I can't lift it at all, then no work's great. Okay, so you can sort of make a case for this, but in a physics sense, you guys know work is like energy, and you can't amplify the amount of energy because that would break conservation of energy. Okay, so energy, work, you can't amplify that. Mechanical advantage, you can multiply your force. All right, Jake, hold on to the lead. How many joules of work are done on a box? Force 25 newtons pushes it for 3 meters. Force times distance. All right, so you guys just know force times distance, right? Force times distance, 25 times 3. Oh, Shane, do the top. How much power to do 40 joules in 5 seconds?
I clicked the wrong one.
Yeah, 8 watts, right? Because 40 joules divided by 5 seconds. Power is a rate of work. It's 8 watts. 8 watts. Yeah. Got Shane, Jake, Natalie, Lucas, Rita. 3 questions left. How much work to move a 30 Newton crate lifting up 2 meters? Yeah, 60 joules. Right. What's the guys? What's the mass of that crate? How many kilograms? About 3 kilograms. Right. So MGH. That'd be also 60 joules of potential energy it would end up with. Right. Ooh, JT hopping in. Shane, hold on to the lead. How much power to lift 60 Newton crate up 10 meters all in 2 seconds?
Whoa.
Yeah, 300 watts, right? So power, you guys know, is work divided by time. And work, you guys know, is force times distance. So here's the force. Here's the distance. So is that 600 joules? Do you guys see 600 joules? Divided by 2 seconds, that's 300 watts. Okay, 300 watts. It's like 3 very bright old style light bulbs. Ooh, Shane on fire on that lead. Last question. Machine puts out 200 watts of power for every 1,000 watts of input. What's the efficiency? Yeah. Okay. Now, last week I gave you guys a different definition of efficiency. In terms of the pulley system, it was, what was it? Like real divided by ideal mechanical advantage. Okay, you guys got that. Right. To the podium. With the bronze. No, Natalie. With the silver. Jake. And the gold. Shane. And our runners up are Lucas and JT. All right, nice job, guys. All right, let's flip back over to page. All right, chapter 5. All right, so last week, I think we just did these first 3 here. Okay, here's some bonus problems. We meant to get to them. Oh, we're on the Daredevil problem. I like this question a lot. So Daredevil on a motorcycle leaves the end of a ramp with this speed. In my notes, of course, I'll change the numbers a little bit. Okay. If the speed is slowed down a little bit at the peak of his path, what is the maximum height that he would have reached? Okay. Notice what they gave you and did not give you. They told you speeds. They did not actually tell you the angle of that incline, did they? Do you guys think that you could, in principle, solve for exactly what the angle of that incline is? Right? In fact, you could probably do that in one step, couldn't you? Do you guys think that 35 meters per second times cosine of that angle would be 33 meters per second? Right? Now that's old physics. That's thinking about projectiles. Actually, let's solve that real fast. I want to do a side quest with that. Let's start with the side quest. So, because I want to tie, because a lot of energy and conservation energy questions, not all of them, but a lot of them can be solved with past physics. And so I want you guys to see how this stuff ties with the old stuff. Okay. So you got, I'm gonna change these numbers. I'm gonna go 25 meters per second. That's a mystery angle, and then we at the top here. I'm gonna call this 23 meters per second. Let's do that. Okay. Could you? Oh, where's my green ruler? Got a gold one. I guess that's the school color. I'll have to substitute for today. What is this height change? Okay. But let's do the side quest first. Okay. So who can tell me what this angle is? I'm gonna calculate it over here. Let's do based on my numbers. Okay. You guys do yours. Sorry, do my numbers. Let's all do my numbers. Once you guys can get this. All right, I got the answer. I know what angle that is. Okay. Who else figured it out? What is that angle? How about this? Okay. See that 25 meters per second? Okay. Yeah. So mystery angle. That's kind of across and kind of up, isn't it? Okay. Now this is not a conservation of energy approach. This is just a side quest. Okay. Okay. Oh, hey, what is this component right here equal to? You guys remember how projectiles work? Isn't there a constant horizontal velocity? Oh, look at that right there. Look at that. Wouldn't this be equivalent to 23 meters per second? Right? Oh, and I have a nice right triangle where that angle, I know the adjacent leg and the hypotenuse. Guys, adjacent and hypotenuse, what is that set up for? Sine, cosine, or tangent? Something to do with cosine, yeah. If this is like 23 meters per second, couldn't I say that cosine of the angle in question is the ratio of what over what? Yeah, adjacent over hypotenuse, 23 on 25. Okay. So then how do you extract that theta? You have to apply an inverse cosine, 23 on 25. The units cancel it out already. Okay. And from that, you get 23 degrees. The number 23 is shown up twice. Okay, that's kind of confusing, but maybe it is 23.1 degrees. 23.1 degrees. Yes. You guys good there? Okay. Since we started on the side quest, let's think the old way to solve for h. Could you solve for the initial speed upward, which would be maybe 25 meters per second times sine of that angle? Wouldn't that be true? Okay. What is 25 meters per second times sine of 23.1 degrees? Okay. That is 9.81 meters per second straight upward. Okay. And then you guys remember an old formula that goes final velocity squared is equal to initial velocity squared plus 2ax. You guys remember that? Okay. We can modify this and say if we're looking strictly in the up direction, this would be y direction, and then this x would just be h, right? Call this h. Would that be true? Right? And then a would be like negative g because it's being pulled downward. Right? Guys, what is the vertical component of the velocity at the very top? How fast is it moving up or down? Right there. 0. Yeah. Okay, so this thing's going to go to 0. Okay. Coming from 9.81 meters per second, strictly upward, initial of that number feeds in right there. Okay. Don't forget to square that. Minus 2 times 10 meters per second squared times the maximum height. I know it's maximum height because at that point it would go to 0 meters per second vertically. Okay. Shuffle this around a little bit. What's 9.81 squared divided by 20? Okay. I'm looking at h max of 4.81 meters. Okay. Now, that's not how you're actually, that's not the intended way to solve this problem, but that's the old way to solve it, right? I just want you guys to see that the new way will get you the same answer, but probably a little bit faster. Okay, you guys ready to see the new way? Okay. The new way is through conservation of energy. So I'm going to do the sum of energy initial is equal to sum of energy final, right? Okay. Now, guys, what kind of energy did that motorcyclist have at the beginning? It's all what kind of energy? All kinetic. 1/2 mv naught squared. And at the very peak has what kind of energy? Both, yeah, both potential and kinetic, right? So some of that energy was routed into his height. So something to do with mgh. And whatever was left over went into speed. And in terms of energy, that's called 1/2 mv squared. But maybe a little subscript f. Is that true? Right? So this kind of energy turned into this and this kind of energy. So this joules equals joules plus joules, right? I mean, these all have to be in joules, right? Okay. Let's plot on some numbers. Actually, oh, we can't because we don't know this guy's mass. So what are we gonna do about that? Yeah, it cancels. I got 3 terms, got the end of all of them. Divide everything by m. You're far. Top of this h. So 1/2 v naught is well, on my paper, in my notes, I did 25 meters per second, so I'll stick to that. You guys can write in your number. Got 10 meters per second squared times sum h max plus 1/2, and then I had my guy slow down to 23 meters per second at the very top, something like that. Okay. Okay. Can you guys do the algebra and solve for that? Okay, so 0.5 times 25 squared, 0.5 times 23 squared. That's like 10. Right. So I'm cutting through some algebra steps here because you guys can do algebra. Right. I'm getting 4.8 meters using conservation of energy. Oh yeah, and then we since we just did the projectile line, going back to projectiles, look at that, 4.81. Probably because there was a little bit rounded numbers in the middle, but you guys see it's the same thing, right? Gives you the same answer. Right. Old way, new way. Okay. Look at that. The old way was this whole process involved a bunch of trigonometry, finding angles, doing like all this crazy stuff. Kinematic form. The new way, sum of energy, energy is conserved. Boom, boom, done. Okay, next, 38. I think it says. 2 blocks connected by a light string passes over a frictionless pulley as shown in this figure. Oh, there we go. This system is released from rest. Well, M2 is on the floor, and let's say M1 is more massive, so you guys see this whole thing's going to rotate counterclockwise. Find an expression for the speed of M1 just as it reaches the floor. Okay, so that'd be in terms of variables. So since we're, well, do that with you guys. And then they give you some numbers, and they say just plug in the numbers. So one thing at a time here. This is number 38. Got this classic double elevator Atwood. Oh, whoops. Well, let's start over. Want to make my picture look like their picture, just so that's super easy to follow. Okay. 38. Okay. There's some little tiny M1 or sorry, M2 down here, and there's a big old M1 up here, and there's some height change. H. Okay. I'll find an expression for. Hold on. The speed, like this crash speed, when it crashes into the floor. Okay. What's the speed it's going to crash into the floor? Okay. See if you guys can stay a step ahead of me. I'm going to try to write this a little bit slower just to give you guys a head start. The sum of energy initial equals the sum of energy final. Okay. Now, the way I wrote this, I'm assuming a closed system. Guys, what objects are in this closed system? This is something that AP could totally ask you. This is a what system. I'm thinking of 3 objects. M1, M2, and the Earth. Yeah, the Earth has to be part of the closed system. That's what's providing a force. Right? Otherwise, it would be considered an open system if you didn't include the Earth with external forces. So, what kind of energy? There's probably a couple of different ways to set this up, but where's the sort of the supply of energy coming from? The fact that M1 is elevated, right? Is that true? So, isn't it all M1GH? Isn't that supplying the energy? Right? Actually, I think we did this one sort of on that table. Right? Okay. And it starts from rest, so no kinetic yet. Right? But where does all that energy go? And I'm thinking of 3 places it goes. It goes into what's one place it goes? Into kinetic of M1, so 1/2 mv squared for M1, right? And also kinetic of M2, that's 1/2 m2v squared. Okay? And also, there's one last place that you have to account for. Yes, potential energy of block 2. Exactly. It has to lift block 2 exactly the same height change, right, that M1 is falling. So that H is that H. And for that matter, that V is that V, isn't it? The fact that they're tied together. They always undergo the same magnitude of height change, and they always have the same speed because they're tied together, right? All right, so the question is, can you solve for this V? And the way I wrote it is, it shows up twice, it shows up there and there, right? But we can just factor that out, right? Okay. Let me do a couple of algebra steps. I'm going to subtract this potential energy term over to the left, and I'll factor out V squared at the same time. So it's going to give me M1 GH minus M2 GH. So that term minus that term. Right? And then I'll be left with 1/2 M1 plus M2 V squared. Okay, so a couple of algebra steps there. You guys get that? You may have just cut straight to the stuff in your mind anyway. I don't know. Be careful about including all the steps for AP. Like, you guys know, if this was an FRQ, AP would be like, oh, there's 1 point there, and there's 1 point there, and there's 1 point there. You know how they add points, right? So definitely write it all out. But in your mind, you guys said, hey, at some collective mass, moving at the same speed. Okay. Oh, it looks like we're just a couple of algebra steps away from isolating that V. Cross multiply by 2, divide by the masses. So V squared is equal to 2 times. Oh, you know what I can do at the same time? Couldn't I factor out GH from both of these terms? So that'd be the difference of the masses times GH. Okay. Then I'll divide it by 1 plus M2. Okay. Yeah, I just have like 2 or 3 algebra steps in there from this line to this line, but I think you guys can follow that. Okay. Take a real good look at that. Okay. And then finally, to isolate V and get the answer, isn't it just let's see if we did this before. This is ringing a bell. Oh, it sure is. To get a nicer handwriting version of that. Okay, I think this one will suffice. Okay. You guys remember this table? This one right here? Look at that, the speed of point B. Isn't that exactly what we just got? That's that, isn't it? Yeah, you guys have seen this before. Okay. Hey, does that look kind of like the form square root 2GH? Huh, like something's fallen, like the Galileo problem? Pop acid bottom, square root 2GH? Huh, that looks like that, doesn't it? Right, well, the mass values would cancel. Oh, and then there was a follow-up question to this, which is they just gave you some masses and a height value and said, solve for stuff. Okay? So, gonna make up my own numbers here. Let's do this. Okay. So the fact that B is equal to that, okay. Let's say that M1 is gonna make up my own numbers, 5 kg, M2 is like 3 kg, Let's call that height change, like 2 meters. Could you guys just plug in stuff and figure out the final speed? Okay. I'll do it here while you guys are, doing it. You can either copy my notes, or you can do your own paper, whatever you guys feel like doing. So it's gonna be a giant square root. Got the difference of the masses, so 5 minus 3 kilograms in this case. Okay. Times 10 meters per second squared, times the height change of 2 meters. And all that divided by the sum of the masses, so 5 plus 3 kilograms. Okay. Okay. Let's see what I get for mine. Okay, so giant square root. Okay. Now I'm going to shove it all into one line in the calculator. If you need to break it down, if you need to like chunk it down into smaller parts and just like write numbers as go along, then that's perfectly fine. 2 times 5 minus 3 times 10 times 2, all divided by 5 plus 3. Okay. And I'm looking at 3.16 meters per second. Oh, you know what? 2, 8. Huh. That's a square root of 10, isn't it? It sure is. Yeah, it looks like a bunch of stuff canceled out there in terms of numbers. All right, guys, good day. All right, next one. Number 53, I think it says. The electric motor of a model train accelerates the train from rest to this speed and this many. Ooh, guys, ms. What is that in this context? What is ms? Like milliseconds, right? Like thousandths of a second. It looks like 21 divided by 1,000 seconds. Right, you guys get that? Okay. The total mass of the train is this many grams. Careful, anytime they give you grams, if you're ever calculating things, you probably first want to convert to kilograms. You guys remember kilogram is the base unit of mass in this car? Find the average power delivered to the train during its acceleration. Okay, well, power is eventually going to be in watts. And remember, kilograms is like one of those ingredients that's baked into the cake of watts. So got to convert grams to kilograms. It's just one of the stuff, right? So 53, that's this model train. So V naught is 0 meters per second because it starts from rest. Let's say V final is, I'll go 0.82 meters per second. Let's say the time interval to do that. I'm going to write delta t. You guys know that can represent time interval, right? How many milliseconds? I'll do 35 milliseconds. Which is the same thing as 35 over 1,000 seconds. Wouldn't that be true? Right? You guys get that? And the mass of the train. I'll make mine 750 grams. But you guys know that would be, how many kilograms would that be? 0.75. Okay, because kilos is a factor of 1,000. Okay. Okay. So there's the 4 values. Now, what power is involved? Well, power is work divided by time interval, right? Rate of work, rate of energy. Right? Huh. And if you went by definitions, then you say, well, work is force times distance. And then you say, oh, we were not given the force and we were also not given the distance. Now, do you think that in principle you could go down a side quest and solve for the average force on that train and the distance that it moved? Like, there are probably enough numbers lying around where you could do that. You could do that approach. Okay. But you know what? There's a much faster way to get this. And this is, I see this as an AP concept too. Sometimes there's like a strict definition way to do it. And there's like, wait a minute, but I know this is equal to this. So there's like a really like fast way to do it. Okay. This is work energy theorem. Isn't it true that the work done on the train is equal to the change in what? Like the change in energy, right? So like the maybe the final energy that it ends up with because it started with 0 mechanical energy, right? So couldn't I do like this? So for the time interval, I could just call it delta t. Okay. So for work, I'm not going to write force times distance. I'm going to say that's equivalent to what expression in terms of the given values? The work you do on something. Let's see, if the train's not moving up any hills, that doesn't give it any potential energy. But it's changing its speed so that all that work is routed into its what? Kinetic energy. So 1/2 mv squared. Okay? Right? So the work you do on it is all going to be routed into its kinetic energy. Is that okay? Okay. So this is the fast way of solving it. So we got 1/2 the mass of the train, and we've done the conversions already. So do this many kilograms. Make sure that the mass of the train's in kilograms. Okay. Times the speed it works up to. I'm using my numbers for the notes. Square. Don't forget to square that speed. Okay. All divided by time interval. So be this many seconds. Awesome. You know what? I think if you looked at the grams and milliseconds, would that actually cancel out? I think it would. Huh. All right. I'm just reading that. All right. So 0.5 times 0.75 times 0.82 squared, all divided by 35 on 1,000. I'm looking at 7.2 watts. Okay. So you need 7.2 watts on that engine. Ooh. Yeah. If you did forget to convert the time and the mass, those two factors do end up canceling out. So you would have got the right answer anyway, but just be careful about that anyway. Okay, you guys go with that? Okay. Oh, we have a graph. A graph. How much time do we have? Till. Yeah. Oh, we got a few more minutes. Okay, I think we got time to do this graph. An object with mass so many kilograms is subject to a force that varies as a function of distance. Guys, anytime you see a force versus distance graph, you guys have seen some of these last week, right? Right? It's almost for certain going to be a question that deals with energy or work, right? Because what property of force versus distance graph tells you work? Remember, it's the area under the curve. You guys saw a few examples of that last week. Right? And that is the question. Find the work done on the force as it moves from this position to this position. You guys know that most of the graphs you guys see in this class have a time axis for the horizontal axis. But if you ever see force versus distance, you're almost for certain going to be asked like how many some number of joules. Okay, and that's the area under the curve. Okay? So from 0 to 5 meters, that's this first segment. From 5 to 10, from 10 to 15. Okay, and then finally they asked something about the speed. Okay, so let's do 50. No, number, what's that say? Number 60? 60. Okay. I'm going to make my own graph, but basically the same questions. We got force in newtons versus displacement in meters. Let's say this goes up to 20 newtons of force, and let's look at 3 meters, 6 meters, 9 meters, maybe something like that. Okay, guys, go with that so far? Okay. So, how much work would have been done during each of these intervals? Okay, guys, what's 3 meters times 20 newtons? What's that? Isn't that 60 joules of energy right there? 60 joules of work, right? And what's 3 times 20 divided by 2? 30 joules, and then the same story over here, 30 joules. You guys see that? Okay. So what's the total work done? You guys see it's 30 plus 60 plus 30 joules, which is 120 joules. Right, you guys see that? That's the total work. Okay. And then the last question was, if you know the mass of the object, then find its speed. Well, it has its speed at different places. I'm going to say the speed at the very end, just for the notes. Right? So if the mass of the object is, let's say 5 kilograms. Okay. Let's say that's also given. Okay. So what's the speed? Speed at the 9-meter mark. Okay, let's figure that out. So also all that work went into its speed. So it got 120 joules of energy, was all rounded into 1/2 mv squared. Okay, so 120 joules went into 1/2 times 5 kg times v final squared. Okay, you guys get that? Okay. So some algebra. What's 120 joules times 2 divided by 5, take the square root. Okay. I'm looking at the speed of 6.93 meters per second. All right, you guys have a good Monday. Don't forget AP Classroom. AP Classroom.